Okay, so in this video we're doing exponential functions. This is one of the types of bread and butter functions that you should know. So exponential functions are of the form y equals, and instead of being x to some power, it's some base a to the power x. So the x appears in the exponent. That's why it's called an exponential function. So a is a positive number. So just like you can't take the square root of a negative number, you can't do the exponential of a negative number in general for any value of x. That's why we got to make sure a is positive. X is any real number. That's saying that the domain of this function is all numbers. Okay, so the next little bit is saying that these are important because they model things in real life. I guess the most famous thing right now is the coronavirus. So the epidemics are often modeled by exponential growth, so it's important to know them. Lots of things in real life are exponential functions. So what does the graph look like? And there's two possible things that it could look like. One happens when you have a base that is bigger than 1, and one happens when you have a base that is between 0 and 1. Let's go back to Desmos and just take a look in Desmos, and we can sort of flip between these. I guess, okay, maybe it's worth doing as a little special case. If you do a equals 1, what does that look like? That's the function f of x is 1 to the power x. That's a boring function. 1 to any power is always 1. So if you did a equals 1, you would just get a straight line that goes through this point 1. So it's y equals 1. And if you have a base bigger than 1, it sort of looks like one thing. And then in between, it's going to look like this flat line. And then it's going to look like something else. So let's open up Desmos and take a look at what it looks like. So we got this base a again. We had that before from the last video, so we can leave that in here. And instead of doing x to the power a, that's a power function. We're going to do a to the power x, and we're going to see what this looks like. So let's zoom out. So this is a is 1.14, and as a increases, you get this big growth. It's growing as x grows. And as soon as you get to a number less than 1, it flips, where it's shrinking down to 0. And in between, it looks like a straight line. So that's what exponential functions look like. For big bases, they look like this. They have this exponential growth. And then if the power a, or the base a, is in between 0 and 1, they have this exponential decay as x increases. And in between, you have this straight line. When a equals 1, you have a straight line. So that's how I remember what's going on in these things, which you may or may not like. When a is bigger than 1, it looks like this, exponential growth. And when a is between 0 and 1, it's like this, exponential decay. So sometimes people call this exponential growth, and sometimes people call this one exponential decay. Okay, and in all cases, it's supposed to go through the point y equals 1 at x equals 0. And that's because if you do a to the power 0 for any power, you get 1. So f of 0 is always 1. Okay, if you know these graphs, I think you know most of the things you need to know about exponentials. There's going to be some algebra as well that'll come up. But here are the properties that you can deduce. So the domain is all numbers. You can do any power you want. The range is only positive numbers. So the range is positive numbers only. This one I already mentioned. The graph always passes through 0, 1. So f of 0 is always 1. And blank, comma a. So when is it passing through a? So we want f of x equals a. That's saying a to the power x equals a. So when would it have a y value equal to a? Well, that would happen when the x value is 1. So when x equals 1, you can retrieve the a value from here. And you can see here it's a little bit higher than 1. That's because a was bigger than 1. And on this side, a is between 0 and 1. It's a little bit lower than 1. So those are two important points to know, I guess, for this graph. So when a is bigger than 1, the function is increasing. And when a is between 0 and 1, the function is decreasing. Y equals 0 is always a horizontal asymptote. So a horizontal asymptote is what you approach when x gets either very large or very small. And in this case, we're approaching y equals 0 as x is getting very small. So a horizontal asymptote over here on this side. And in this case, we're approaching y equals 0 when x is getting very large. So that's a horizontal asymptote on the other side. Okay, why do we require a bigger than 0? The problem is that for a less than 0, certain choices of x result in complex numbers. So for example, if a is -1 and x is 0.5, then you have -1 to the power of 0.5, which is also known as the square root of -1. And we are not doing any complex numbers in this particular course, so that's why we're not considering the case a less than 0. In a different course, you might do that. So for now, we're going to stick to a bigger than 0 to keep things nice. Okay, and also look, this exception I mentioned is also mentioned here. A equals 1 is an exception since y equals 1 to the x is just a constant function. Okay, good. So that's about the graph of exponentials. The next important thing to know about them is these algebra rules. So how to manipulate exponentials algebraically. And here are all the possible algebra rules that you can get, and they tell you how to simplify certain things. So for example, if you do a to the minus x, when you do a negative exponent, that's doing a reciprocal. So this is 1 over a to the x. Similarly, if you do 1 over a to the minus x, then you're going to just get a to the x back. Here's one people mix up a lot. A times b to the power x, that's the same as a to the x times b to the x. Same kind of thing with division. A over b to the power x is a to the x divided by b to the x. Here's another one. If you're multiplying in the exponent, then you can put brackets around it in two different ways. So you can do a to the k to the power x, or you can do a to the x to the power k. And those are all the same. So multiplying over here, it factors out of the brackets like this. And when you multiply inside the exponent, then you can put brackets around it as exponents. So you have to sort of remember these to get them straight. I do think it is worth your time. There's not too many things in this course that are like you really have to super memorize, but this is one of them where I think it's worth your time to memorize this so that you can do it really quickly when you're in the middle of a big complicated problem. You have to use this fact. It should be easy for you to do. Okay, here are some more. So if you do the same base a to the power m times a to the power n, that's the same as a to the power m plus n. So multiplying the same base is adding the exponents. Okay, so again, I think it's worth your time to memorize this one and be really, really comfortable with it. If you're ever confused, you have like a little moment, you're like unsure, did I do it right? Because it's easy to confuse like something like this with something like this. Maybe you get mixed up. So the way I remember them, if I'm ever confused and I want to like really be 100% sure, did I get it right? I think of a to the power m is a multiplied out m times. So a to the power m is a times a times a m times. So we have m a's over here. And then a to the power n is a n times. So it's a times a n times. So we have m copies of a in the first bracket. We have n copies of a in the second bracket. So what happens when you multiply them all together? Well, when you multiply them all together, you do the first m, and then you do the next n. So how many are there in total? In total, there's m plus n a's here. So that's why this whole thing is equal to a to the m plus n. And that's how I remember it. If I'm ever sort of like worried for a sec that I did it wrong, that's how I remember all these rules. So all these rules are logical rules that come from just like what you're used to in multiplication, but they're sort of packaged maybe in a way that's scary. So you do kind of have to memorize them, but it's helpful maybe for some people to do it this way. Sometimes when I show people this, they say, why are you making it so complicated? Just remember the rule. So if you think that's complicated, just remember the rule, I guess. Similarly, a to the m divided by a to the n, that's a to the m minus n, and that's because if you have m a's on top and you have n a's on the bottom, then you can cancel out n of these things. So the m's will subtract, the n's will subtract from the n. That's why you get a to the m minus n. Okay, again, if you don't like that, just ignore it. All right, here are some more. A to the 1 over n is the nth root of a, and a to the m over n is, you can write this as a to the 1 over n to the power m. That's the rule for multiplying things, which is the nth root of a to the power m. And you can bring this in and out. So you could do the nth root of a to the m as well. Okay, so those are all the rules for simplifying. There's one more sort of logical rule, which I'll go over in a second. But these are the rules, and you're going to be using them a lot. So if you're a little shaky on these, it's totally fine. That's why we have on Mathematize, there's a whole bunch of questions like this that you should practice and get a feel for. And you sort of get marks for doing it. So it's a good win-win. If you are uncomfortable with these, it's no problem. You have lots of time to sort of get comfortable with them. Okay, last rule, if a to the m equals a to the n, for every a except for 1, then m equals n. So when a equals 1, you have this exception that you're the constant function. But other than that, when two exponents are equal, when two exponential functions are equal, a to the m equals a to the n, the values m and n must be equal. So we'll use this sometimes in doing problems. So this last one is maybe a little different than the rest. It's not simplifying. It's like a little logical step. If a to the m equals a to the n, then m equals n. And there's this dumb exception of a equals 1. So you got to keep that in mind too. Okay, those are the rules. Let's do some practice with them and see what's going on. Oh, okay, before we do practice, there's one special base, the base e. So a very special base is the base e, where e is just a constant and it has a non-terminating decimal expansion like pi. So pi is this famous number that goes on forever. E is just like that. I believe it starts with 2.718, but let's see if I'm right, because I'm not very good at memorizing numbers. So let's see let's see how close I was. If I go to Google, I type in E. Okay, wait. I don't want any of this. Let's start over. Let me try again. What a disaster. Let's cancel. Actually, does Desmos know what E is? Oh, there we go. Look, Desmos knows what E is. I don't even need to use Google. So if you put in E in Desmos, it knows it's 2.71828. So did I get it right? 718. Okay, that was pretty close. So here's my favorite fun fact about E. All right, maybe this is like a little bit out of the way. So if you're sick of fun facts and you just want to learn the review stuff you have to learn and you don't want any fun facts, here's my fun fact about E. E is the average number of dice rolls E is the average number of dice rolls you need. So the sum of dice is greater than the number of sides on the dice. So for example, if you're rolling 6-sided dice, how many dice rolls do you need until the sum of the dice is more than 6? Well, 1 dice roll surely will not do it, because you can roll at most 6, so you haven't gotten over 6. So 1 is definitely not enough. 2 is often enough. So if you roll 2 dice, most of the time it comes up with a 7 that's bigger than 6. So 2 is enough most of the time. And sometimes you need 3 dice rolls. So if you roll 3 dice, you're very, very likely to have a sum more than 6. So that's for 6-sided dice. The same kind of thing works for 20-sided dice. 1 dice roll, not enough. 2 dice rolls, probably enough, but maybe not. 3, almost, definitely enough, but maybe you need more. And E is the average number you need. So that's why E is sort of between 2 and 3. 2, not always enough. 3, most of the time is enough. And that's why E is between 2 and 3. And this works if you use an infinitely sided dice. So for 6-sided dice and 20-sided dice, it's not exactly true, but the more sides of the dice you have, the closer and closer you get to this value of E. So maybe I'll say it's this for an infinity-sided dice. So that's my favorite fun fact about E, which you guys now all know. Okay, so welcome back to everybody who skipped over that little side note about E. And we're going to find out lots of special things about E in this course. So that's one of them, was this funny dice roll thing. But there's more simple things that are special about E. There's a reason it comes up all the time in calculus class. All right, but you don't need to know anything special about it right now. The shape of the function e to the x is the same as 2 to the x. Anything bigger than 1, anytime the base is bigger than 1, it's going to have the same shape, and E is no exception. So it looks like just the usual blowy up E thing. Okay, that's it for exponentials. I think we can do logarithms in the same video. Actually, why not? We're already doing a bunch of videos. Let's do logarithms in a separate video.